Welcome back to the last session of today's schedule. Let me invite Professor Aveek for giving this talk on scaling quantum Hall regime.
Thanks, Amit, and thanks to the organizers for this wonderful conference. So today I will be describing our recent experiments on scaling in the quantum Hall regime. So just a brief introduction. We are a group which works on topological phases in graphene-based heterostructures. We induce several interactions in graphene, spin-orbit coupling, Moiré superlattice, exchange interactions, and of course we study fractional quantum Hall. These are the people we collaborate with. And let me start by acknowledging the funding. Simran, who is here, she has done majority of the work that I will present today. Tanima, Kazi, and Yuval and Srijit helped us with the theory. And the boron nitride, as usual, is from Watanabe and Kanikuchi. So in condensed matter, we look for the fundamental states of matter. And in the quantum world, we have metals, insulators, superconductors, magnets, and they are all differentiated by broken symmetry. So some cases you break time reversal, crystal, phase, as Mandar pointed out. So, but these are all quantum but not topological states. So what are topological states of matter? Topological states of matter are states where I cannot go from one state of the system to another without breaking some kind of a topology. So there is local perturbations cannot take me from one phase to another. And they are characterized by a number of topological properties. Examples are quantum Hall, quantum anomalous, quantum spin Hall. And today I'll be talking about quantum Hall, which is probably the prototype of the topological phases of matter that we know about, characterized by the Chern number. That's its topological number. So just to give a few slide introduction to people, of course, most of you know about it. So let's think of a two-dimensional electron gas. I apply a magnetic field perpendicular to its plane, and I can measure two quantities, Rxx, which is a longitudinal resistance, and Rxy, which is a transverse resistance. And at high temperatures or in the classical regime, Rxx is independent of magnetic field, Rxy goes linear as the magnetic field, just a measure of the number density, nothing fancy here. But as I lower the temperature or increase the magnetic field, something beautiful happens. The Rxx now starts oscillating, going to exactly to 0 at certain values of magnetic field. And at these precise values of magnetic fields, the Hall resistance now gets quantized exactly to values of h by e square. Okay, so 1, 1/2, 1/3, 1/5, and this quantization is accurate to parts per billion. So the conductance is nu e squared over h, where nu is the ratio of the number of electrons to the number of flux quanta of the system, and it's an integer, while the conductance and the resistance are both identically 0. Now, why does it happen? Well, as you know, when I put a two-dimensional electron gas in a magnetic field, I develop these so-called Landau levels, and I can start thinking of, as I increase the magnetic field, I start filling these Landau levels slowly and slowly. So let's look at this case, where I have two Landau levels which are completely filled. The chemical potential is lying between Landau level 2 and 3. In such a situation, my conductance will be 2 e squared over h. And my Rxx, which is longitudinal conductance, is identically 0. How do we understand this? Well, we can understand this from a single particle picture. So I have two completely filled Landau levels. These are the two filled Landau levels. This is my chemical potential. So in the bulk, there are no states in the chemical potential, and therefore no currents can flow in the bulk. However, at the edges of the sample, I have this confining potential, which causes these Landau levels to curl up. And wherever these Landau levels curl up, this chemical potential now intersects these Landau levels. And because it's a filling factor 2, I have two states. I have two one-dimensional edge channels near the physical edges of the device. And each has a conductance of e squared over h. So the Hall conductance gets quantized to e squared over h times the number of edge channels, which is again the topological Chern number of the system. Since these are dissipationless channels, your longitudinal resistance is 0. So, but this is not the whole story. When people started making better devices, they went to lower temperatures, they went to higher magnetic fields, they start seeing that the conductance can now, the Hall conductance can now get quantized to fractional values of nu. It's nu e squared over h, where nu equals p by q and p and q are co-primes. So this, of course, you cannot understand from the single particle picture. This arises because of electron-electron interactions, which opens gap in the Landau levels. So this is the regime that I am interested in my presentation today. So how do I understand the fractional quantum Hall? Let's take the example, probably the most trivial example of nu equal to 1/3. In this state, the number of flux quanta is equal to 3 times the number of electrons. So Laughlin's insight, for which he got the Nobel Prize, was that, well, let's attach 2 vortices to each of these electrons, and we call them flux quanta. So what he essentially did is that he took a strongly interacting electronic system, attached 2 flux quanta to it, made it into a quasi-particle, a weakly interacting set of quasi-particles, which he called a composite fermion. Now, for every composite fermion, I have 1 flux quanta left. So this is like the Landau level 1 of the integer. So what this procedure does, it takes a fractional quantum Hall effect of the electrons and converts them into the integer quantum Hall effect of the composite fermions. So the filling factor of the composite fermions is given by 1 by twice nu plus 1. Here this nu is a topological number again of the integer quantum Hall. And this gives the so-called Laughlin sequence. You can add 2 flux quanta, get 1/3. You can add 4 flux quanta, get 1/5, 6 flux quanta, and so on and so forth. But this again is not the whole story. You have these other fractions, 2/5, 3/7, so on and so forth. How do I get it? Well, 1/3, you can think of adding 1 composite fermion per flux quanta. This is the filling factor 1 of the composite fermions. Come to filling factor 2/5. This is 2 composite fermion per flux quanta. This is the filling factor 2 of the composite fermions. 3/7, I have 3 composite fermion per flux quanta. This is the filling factor 3 of the composite fermions. So you can take any of these fractions, all these odd denominator fractions, and you can transpose them into a integer quantum Hall picture. Okay, you can forget about the interactions, and whatever you know about the integer quantum Hall, you can carry over on to the fractional quantum Hall. Well, most of it. And this gives you the so-called Jane sequence, 1/3, 2/5, 3/7, and this is how you explain all the odd denominator fractional quantum Hall systems. Now, this is all the story about the edge states. The question you ask is, what is happening in the bulk of the system? So suppose my chemical potential is here when one of the Landau levels is half filled. In such a situation, your Rxy is not quantized. It's lying here between these E squared over h and half E squared over h. And my Rxx has a maxima. So what is the physics of this part of the story? Well, let's look at the Landau level picture of a clean system in large magnetic field. You have this spiky, almost delta function like Landau levels separated by the h bar omega c. But that's not a real system. In a real system, I always have disorder. And as you know, in 2-dimensional system, even a small amount of disorder will give me localization. So what happens is that you have these localized states. Almost all the states in the Landau level are now localized, except a very narrow patch of states in the center, which are extended. So as I move my chemical potential across, I go from an extended state to a localized state to an extended state. So the transition between an extended state to another extended state has to necessarily pass through an order-disorder Anderson kind of localization transition. And this is a continuous phase transition. So whenever you have this continuous phase transition, of course, you have an order parameter, you have these critical exponents. For example, you can ask yourself, how does the localization length vary as I move from one plateau to another? And you can see here that the localization length, since it's a second order phase transition, it will go as nu minus nu c, where nu is again the topological quantum number and with an exponent gamma. And that is what we want to measure. Okay? And of course, in reality, the localization length will never diverge. It will always get cut off by an effective length, which can be the real size of your sample or the phase coherent length or some other length scale in the system. You can, of course, also define the coherence time, which is in some sense the shortest time scale in the system. The system, it's in a critical state, so there is a critical slowing down of the system. All time scales diverge, and that time scale is given by this dynamical exponent z. So this z, which is the dynamical exponent, gamma, which is the localization exponent. And these are the two exponents which characterize phase transition or a continuous metal to insulator phase transition. And this parameter kappa is given by 1 by gamma z. So this is what we want to know. Now, let's look at kappa, how you can get it. Well, to get kappa, use what is known as a finite size scaling relation. So you measure the Hall resistance and you say, well, there is a length scale L, which goes as 1 by gamma. Now this finite, because it's a finite size scaling, L can be the size of your sample, it can be the coherence length, it can be the localization length. And after some mathematics, you find that the derivative of the conductance with respect to the filling factor goes as T power minus kappa. So you take this Rxy, you take the slope, and the slope will go as temperature to the power minus kappa. That gives you one method of measuring this exponent kappa. You can also measure the Rxx and measure its half width at full maximum. That also goes as T power minus kappa. So these are two independent ways of measuring kappa. And the theoretical measurement, theoretical estimates from numerical calculations based on the percolation model, the Chalker-Coddington model, is 0.42. Now the question we asked is, what about scaling in the fractional quantum Hall regime? Can I really think of a transition from a fractional state to another fractional state again as a localization delocalization transition? And a recent paper by this group said that yes, we can do it, provided the composite fermions are weakly interacting so that the localization physics is identical in the fractional quantum Hall as it is for the integer quantum Hall, and then they should have the same critical exponents. Well, this was the first result, not from R. This is the paper from Mansoor Sagan's group in Princeton. This is their fractional quantum Hall. They measured the value of kappa for 3 different samples, and the values of kappa are all over the place. So this is what is expected, and they get it everywhere. Okay, it's not close to 0.42. So we understand what the problem is, and this is a compilation of data from over 40 papers over the last 30 years in this field. And you can see that this is the prediction, this is the data. Okay, so for gallium arsenide, mercury cadmium telluride, quantum wells, heterostructures, even in graphene, the data is all over the place. It's a complete scatter, complete mess. So we started thinking, what is the cause? And we think we understand. The cause of deviation from kappa is a long-range nature of scattering. So when you're talking of an Anderson localization, delocalization transition, you're talking of non-interacting particles. I cannot have a scatterer whose potential is so broad that the fluctuations between the particles is correlated. That is what I have to avoid. Okay? So in gallium arsenide, for example, you have this aluminum gallium arsenide alloy, which creates these correlated long-range disorders in the system. So an experiment was done in 2005 where they showed that if I vary the aluminum concentration at very large aluminum concentration where I have clustering of the aluminum alloys, and at very low aluminum concentrations where I have ionized impurities, the value of kappa is deviating from the ideal value. And there is a very narrow region where kappa is 0.42. So this was not satisfactory for us. We thought, okay, let's do the experiments and try to find out what is happening. So this was the first thing, the kappa, the localization exponent. Now let's try to think how we can measure the gamma, which is the exponent which controls the divergence of the localization length. So for that, you come to these localized scales and you measure the conductance. And in this regime, the transport is dominated by a variable range hopping of the Ifrov-Shklovsky type. So you calculate this conductance. You know, in the variable range hopping of the ES type, there is a Coulomb gap near the Fermi energy, a soft gap. The gap depends on the value of gamma. So if you can measure the conductance, you measure the energy gap, and you can extract gamma from there. And people have done this in gallium arsenide, and you get gamma equal to 2.3 in agreement with simulations. So to summarize so far, scaling exponents characterize the plateau to plateau transitions. Results of scaling exponent kappa is inconclusive, even in the integer quantum Hall regime. And we know this is because the results are marred by long-range impurity scattering, which is very difficult to screen off in gallium arsenide devices. There are some current attempts being made to put heavily doped metals as gates, but the results are not very encouraging. And of course, there is no result of the localization exponent gamma or the dynamical exponent Z in the fractional quantum Hall regime. So these will test actually how much the law of correspondence between the fractional quantum Hall and the integer quantum Hall holds. How much can we take the Jane and the Laughlin picture seriously? So our system of choice is an ABA trilayer graphene. I will tell you why we chose an ABA trilayer graphene and not the simple monolayer graphene. This has 3 layers here. And if I look at the band structure, you see it has 2 kinds of bands. The red ones show a linear dispersive monolayer-like bands, and these blue ones show, at least near here, are the quadratically dispersed bilayer-like bands. Okay? And this plane is the mirror symmetry. So when I don't have a vertical electric field, the system has a mirror symmetry which protects these monolayer-like bands and the bilayer-like bands from mixing. So these sectors are completely decoupled. When you apply an electric field, you break this mirror symmetry and you allow the band structure changes, you develop these gullies, these dips, trigonal warping-like states, and you allow these sectors to change. So applying an electric field in the system is a method of allowing band structures to mix. And that is what we wanted to check. What is the effect of band structure mixing on fractional quantum Hall regime? So this is the energy dispersion relation. The blue lines which you see are the Landau levels coming from these blue points, which are the bilayer-like sector, and the red lines are the Landau levels of the monolayer-like bands coming from these 2 points, the monolayer sector. And we perform our experiments in this narrow region where there is no Landau level overlap. Now, as soon as I apply an electric field, this diagram becomes crazy. And you can see that all these levels start overlapping with each other. And that is what we want to see. With increasing electric field, as these levels overlap, how does the physics of the fractional quantum Hall change? So this is the device structure. We have an Bernal stack trilayer graphene encapsulated by HPN. We put graphite gates on both sides. This is the device structure. And this is the resistance versus number density. The mobility is around 40 meters square per volt second, quite good for these kind of devices. The impurity levels are pretty low. And so why did we choose graphene? In graphene, I can have a system where I can put a metallic gate between the graphene and the source of long-range scattering to screen it. In graphene, the source of long-range scattering will be the dangling bonds from SiO2. So the first device which we make is, we have this hexagonal boron nitride encapsulated graphene directly on silicon dioxide. This will suffer the long-range scattering from the charge impurities of silicon dioxide. You measure the kappa, and you see that the kappa is all over the place, 0.63, 0.5, 0.44, and it differs for different samples. Even in the same sample, in different sets of contact, you measure different. It's non-universal. And we know the culprit is long-range disorder potential. So what you do, below the bottom HPN, you put a graphite gate to screen off the impurity potential scattering from the SiO2. Okay? And then you see that immediately for the integer quantum Hall, the kappa becomes 0.42, and it matches the theoretical predictions immediately. So next, what do we do? Well, you can play the game. You can take the second derivative. And from scaling, you know that the second derivative will go as t power minus 2 kappa. And you see that the slope is 0.43, 2 kappa, giving you a kappa of 0.41. You can take the second derivative, third derivative, and everything matches with the theoretical predictions. So now, what about scaling in the fractional quantum Hall regime? This is the data that Simran got in her trilayer graphene device. We actually have a better device which we are measuring now. So these are all the fractions which you see. And so let's look at the transition from 8/3 to 13/5, which is like from 1/3 to 2/5. Okay? And this is the critical point. You first identify the critical point where all these isotherms intersect. And this equation of the critical point is given from this equation. So this is theoretical critical point. This is measured, and we see that they match exactly well. So there is, first test, there is a critical point between two transitions between two fractional quantum Hall states. Then you take this, you take the derivative, you plot them versus temperature, and you get the exponents. And you see that for integer, for example, I'm showing here from -1 to -2, kappa is 0.40. From 8/3 to 13/5, the kappa is 0.42. So the scaling exponents between the integers and the fractions are the same. So, excuse me. So now the data which I'm showing you in the previous slides is between 200 milliK to 1.5 Kelvin. And the fractions survive till around 20 millikelvin. The reason is that at lower temperatures, this derivative saturates. Okay? So remember, I'm doing a finite size scaling, and at low temperature, I have a finite size of the sample. I always have a finite size of the sample, which is around 5 to 10 micron. At low temperature, the coherence length, the localization length, everything becomes larger than the sample size. And my sample size becomes the dominant length scale in the problem, and it cuts off all scaling. So at low temperature, the scaling does not work. Everything becomes flat. This is the sample size. So I have to do the scaling only in a very narrow range at in the high temperature range. So this has of course been seen previously also in integer quantum Hall regime. So now, how do I can also do a scaling using the width of the Rxx. So this is a measurement of Rxx as a function of temperature. You calculate the FWHMs, you plot them versus temperature, and the exponent kappa here turns out to be 0.43. So there is a third method. You can try to do a finite size scaling analysis. So this is the scaling equation. Rxy will be a function of some parameter alpha, which goes as t power minus kappa, nu minus nu c, when nu c is the critical filling factor. So what we do is, we take this data at different temperatures, we choose kappa, and we try to make the plots collapse on top of each other. And we try to find out the least square deviation between these fits. So you can see at 0.25 the collapse is bad. At 0.43 the collapse is visually good. At 0.6 it's even bad. But visually it's very difficult to distinguish between 0.4 and 0.45. So we do an error analysis. And you see that on a log scale, the error is minimum at 0.41. which tells you that the finite size scaling is a very good method and the kappa exponent is 0.41. So, and once you do that, the data from all temperature ranges from 0.4 Kelvin to 1.3 Kelvin, they collapse into a single curve, telling you that the finite size scaling is really happening. So this is our data, the value of kappa for several fractions for the integers. And just to put things into perspective, all this scatter was the previous data. These are our data points. Okay, and this dotted line is the theoretical prediction. So now that we have a good hold on the kappa, we went on to measure the. Okay, the next question you ask is, when I apply an electric field, as I told you, I start mixing the monolayer and the bilayer bands. It breaks particle symmetry around nu equal to half, and this is an advertisement. Simran will give a talk tomorrow on this at 12:30, and it also leads to the emergence of 5-half and 7-half fractional quantum Hall states in this system, which I'm not going to talk about today in this. But it's exciting because then it opens up the possibility of having non-abelian states in trilayer graphene, which we are currently exploring. So you want to look at the value of kappa with an electric field, and you see that it changes but not that much, which tells you that as long as the fractional quantum Hall states form, the order-disorder transition does not depend on Landau level mixing. The basic physics remains the same. Now, of course, we have determined kappa. I now want to determine gamma. And then I can, of course, get the dynamical exponent z from this equation. How do I get gamma? I go back to this equation, to this plot, and I try to see what are the charge carriers doing in this localized regime. So I know that in the integer quantum Hall regime, in this region, transport takes by variable range hopping of electrons. That is very well established. Question is, in the fractional quantum Hall regime, do I have some kind of a variable range hopping? What decides the transport in this localized regime? And if there is a hopping, which is the entity which is doing the hopping? Is it electrons which are hopping? Is it composite fermions which are hopping? What do I even mean by composite fermions hopping from place to place? Because these are quasi-particles. So this is the question we start to ask ourselves. So we say, while we don't know what is hopping, but we assume that there is some, because the data shows that there is some kind of hopping transport. So we assume that the transport is of the Ifrov-Slopsky variable range hopping type. I do not know what is hopping. Something is hopping. And I take the data and I fit the slopes, okay, and I get a gamma to be 2.21. The prediction is 2.23. This is the same as for the integers. And from these ratios of the gamma and the kappa, I get the dynamical critical exponent to be 1, as it is theoretically predicted. So Okay, I am over time, but let me summarize. We observe a super universality between the integer quantum Hall and the fractional quantum Hall states. What we mean by that is that the integer quantum Hall we understand, the plateau to plateau transition we understand as an Anderson localization delocalization transition, where I have an extended state, I have a mobility edge, and the carriers must cross that mobility edge to reach the next extended state. This is a continuous phase transition characterized by some critical exponents. The scaling exponent kappa, which is numerics tell us it's 0.41. The scaling exponent gamma, which numerics tells us is 2.3, and the dynamical exponent, which physics tells us is 1 for a clean system. So what we show is that there is some sort of super universality where the integer quantum Hall and the fractional quantum Hall transitions are governed by the same critical exponents. Now this is surprising if you think of it, because integer quantum Hall and fractional quantum Hall, the quasi-particles are completely different. In integer quantum Hall, I can understand very well in terms of non-interacting electrons. Fractional quantum Halls, the transport I understand in terms of composite fermions. They have very different statistics, they have very different distribution functions, but yet when it comes to a basic, something basic like this plateau to plateau transitions, they obey the same critical exponents. We also find that when I go from an integer to a fraction, the critical exponents are the same. So it looks like it, as long as Anderson localization delocalization is concerned, it doesn't matter which entity is hopping. It can be electrons to electrons, it can be electrons to composite fermions, it can be composite fermions to composite fermions. The results are the same. Scaling analysis validates the corresponding. So this is the law of corresponding states, which tells you that the physics of nu equal to 1/3 can be mapped into the physics of nu equal to 1 of composite fermions. We validate that. We validate the finite size scaling analysis of fractional with a critical scaling exponent 0.42. The same critical exponent, the gamma for fractional quantum Hall and the integer quantum Hall. And the dynamical exponent Z is the same for both integer quantum Hall and the fractional quantum Hall. So the next step that we are going to do is we are now going to look at the scaling exponents for the 5/2 state to understand whether the physics of the 5/2 state is any different from the standard fractional quantum Hall or the integer quantum Hall state. Okay? So this is something which I wanted to show you in different configurations. They're same, but it's not important. So the paper is here recently in the archives. So if you want details of the data and the measurements, please have a look, and thank you for your attention.
So thanks for the nice talk. Questions?
Hello. I have two short questions. One is that in general, this is a little bit more philosophical in the sense that when we think about localized states, in integer it is very easy to think that I know what orbiting and what.
Yes. Yes. Is there a way to think about this localized state? So this is what we have been trying to do. So let me just go back a few slides, and that information is hidden there. Let me see, this is the Coulomb gap, T0. Okay. Now I can measure T0. Okay. I know nu C, and I assume that xi0, the localization prefactor, is of the order of the magnetic length. Okay. Then I can ask myself, what is E? I know C, what it will be for a 2D material. I can ask myself, what is C? So for a fractional charge, for example, in 1/3 C, E will be 1/3, right? I can also ask myself, when I calculate the magnetic length xi0, it's h bar by EB. What do I take E? Is it the effective charge or the electronic charge? Okay, so whose magnetic length I'm talking of? So when I do this, and this we have done in I'm not very confident of it, but this matches very well when I take the fractional charge. So it looks like it's a fractional charge which is hopping, but I do not know physically how to think whether an electron hops along with two flux quanta or it hops and there picks up two flux quanta. That mental picture is not clear for me yet. Yes.
But as long as you don't change the filling fraction, the wave functions remain same up to some
That's what we wanted to text. Absolutely. So the reason why we did was that, and that's probably Simran will talk about it tomorrow, is that at low electric fields, we have this 1/3, 2/5, 1/3, 2/5, 3/7, and all these 2/3. As we increase the electric fields, in the recent experiment, she starts this 2/5, the 5/2 plateau the plateaus developing. So then the question is that 5/2 is a lambda level 1 physics. So, but here I don't know what is the physics. So am I changing the orbital nature of this thing? That was our motivation. So, but we can discuss it. Thank you.
So regarding the first question, you can look at this paper by Srijit, J.K. Jain, etc. Right? So that might have some details. Yeah. More questions?
Yeah, nice talk. So what is the electric field you apply to measure the Hall resistance? What is the magnitude?
The in plane?
The outer plane electric.
Outer plane when measuring. So the mixing begins at what, 0.2 or 0.3 volt per nanometer.
And the longitudinal resistance increases as a function of, with increasing the displacement field, right?
Well, we are in the quantum Hall regime, so it does not depend on that.
Okay.
You're right. If it was a normal trilayer graphene, if I was in zero magnetic field, gaps will open up and we see that. But it's not, in trilayer, it's not that simple, right? You have these multiple Lifshitz transitions which the system undergoes. So it's a non-monotonic function of the electric field.
So there is no mixing between XX and XY?
No, there is no mixing.
Yeah, so one small question. When you're considering the fact that, okay, fractional quantum Hall states are going to be described by a particular universality of phase transitions, right? Even denominator and odd denominator fractional quantum Hall states have different origins. So any particular reason to believe that they will have the same universality, or like
no, I'm not assuming anything now. We will measure and see.
Okay.
I have no idea what I will see in the even denominators.
Okay. So
we will measure and maybe next year I'll answer your question.
Okay, sure.
Yes. Oh, we see all the filling factors. And now in the new samples, we have even more. So we have 5/2, 7/2, 3/2, I think. So yes, this was a very good device.
So the only difference between your data and all the other scatter plots that you showed was the screening. Of the SiO2. So if there are no other questions, let's thank Aveek once again for the very nice talk.